Welcome back. We were discussing the fundamental of electronics on the topic BJT, that is Bipolar Junction Transistor. We will take the discussion forward and discuss the concept of biasing in the BJT. So, what is the importance of BJT biasing for the concept of amplification? Because we have not taken amplification in detail. In the coming lectures, we will discuss more on amplification. So let us discuss what is the concept of biasing. So the definition goes like this. The BJT biasing will involve setting up a transistor amplifier for desired operating conditions. So we will be setting the conditions where the amplification process will be effectively carried out, and this will be done with the help of applying a DC supply to the different terminals of the BJT. So what is the purpose? It will establish the DC operating point and it will ensure that the stability analysis variations do not take place due to the temperature changes. Amplifier analysis components, we have the DC analysis where we determine the steady state operating point, and in the AC analysis we determine the response due to input signal. We apply the concept of superposition where the DC and AC analysis can be handled separately, and the energy transfer that take place due to the signal amplification in the AC is powered by the energy from the DC supply. So the DC supply is a must for the BJT operation, and it will amplify the signal which is the input, that is the AC signal. So the interdependence, when we talk about the DC operating point, affects the AC response and vice versa. So whatever the DC supply we are giving and the point of operation, that will affect what is the AC response that we are getting, and it is vice versa also. So the biasing and its significance. Biasing is just the application of DC voltage to establish a fixed current and voltage level, and we have seen that we estimate the Q point. This was discussed in much detail in the previous lecture. So the Q point is nothing but the quiescent point, which is the operating point on a device characteristic where the system is stable and inactive without a signal. So we are trying to find the point of stability in the BJT operation. So the purpose we have that it enables the transistor to amplify the input signal effectively. So the amplification which we need to achieve for the BJT, it should be effectively done in the Q point without having any variation. So the real world cases when we talk about, then we have audio amplifiers, RF circuits, signal processing amplifications. Some of the common biasing techniques that we will discuss in this topic, we have the fixed biasing, the emitter bias, the voltage divider bias configuration, the collector feedback, emitter follower, and common base. So these common biasing techniques we will discuss in this particular lecture. Let us discuss the revision of some of the important facts. So we have seen some of the basic equations that is used for transistor operation, where the base emitter voltage for a silicon transistor we take 0.7 volt. The emitter current is beta plus 1 times the base current, which is approximately equal to the collector current, and collector current can be taken as beta times the base current. So beta being the gain. So this basic equation and the derivation we have seen in the previous lectures. Here the base current is usually determined first. So we will determine the base current and then only we will get the collector current or the emitter current. The key biasing requirement for the amplifications are, you should have the forward biased for the base emitter junction. The base collector junction will be reverse biased, and we need to maintain the operation in the active region for effectively signal processing. So we should know which terminal is forward biased and which junction is reverse biased, and the operation in which characteristic we need to do, that is the active region. Temperature plays an impact because it will increase the leakage current and it will also alter the current gain. So temperature will have a significant impact on the operation of the transistor. The stability factor, which is a measure of the effect of temperature on the Q point stability, and it is higher stability is highly desirable for the BJT operation. So in order that the temperature do not change the BJT operating point, we need the transistor has to be stable, and for that we need biasing. Q point analysis we have done. Basically, we have seen that when we draw a curve between the collector current and collector to emitter voltage for a fixed value of the base current, then we basically get the curve which is in the active region. So here we have different points which we can think of, like point A if we see on the curve. So here the device is completely off and this is unsuitable for the amplification process. In this point A, if we see the collector current is 0 and collector to emitter voltage is also 0. If we see the point B on the curve, this is basically ideal for the small signal amplification due to the linear response. So here the response is linear and this point is quite suitable. If we see the point C here on the curve, then it is basically limited to swing and non-linear response. So point C is due to the swing and non-linear response, whereas point D if we take on the curve, this is because of high voltage operation and it is limiting positive voltage swing. So we can say that the point B, which is very much suitable for the amplification process, it ensured uniform amplification over signal swing and it maintained consistent device gain. It also maximized at point B without crossing into cutoff or saturation. So we have the region which is the two, apart from the two active region, you have the cutoff region and the saturation region, and your point B is usually lie in the active region where the device amplification process will take place. So the first configuration, which is our topic for today's lecture, we will discuss on fixed bias configuration. Lecture 6B and 6C, we will discuss the other type of configuration. So fixed bias is basically the simplest. It is the DC bias configuration for a transistor and it can be applied to both NPN transistor or PNP transistor by just changing the direction of the current and the voltage polarity. So if we see the fixed bias circuit, so in the base we have a collector and we give the AC input signal. On the collector side we have a capacitor which takes out the AC output signal. Now this is the DC equivalent circuit of the fixed bias circuit. So for DC analysis, what we do is that the AC sources are removed. So we have the AC sources, AC input signal. It is removed by replacing the capacitor with open circuit. So we have two capacitors C1 and C2. These are basically replaced with open circuit in the DC analysis. And the source, which is the VCC, it is basically split into the input and output sections. So this is basically the input section and this is the output section. So we have splitted the source into two sections for simplifying our analysis. We can say that the capacitive reactance, we know that Xc is equal to 1 by omega C and omega is nothing but 2 pi f. So when we have the DC analysis, the frequency is 0. So if the frequency is 0, then the capacitive reactance will be infinite because we know that 1 by 0 will give you infinite. So capacitive reactance become infinite, or otherwise we can say it is very, very high value of the reactance. If we do the analysis in the base emitter loop and apply the KVL equation, so we can write all the voltages that you have, summation of all the voltages in that loop to be 0. And this is written in accordance with the Ohm's law. So the base current equation we can get from this equation, what is IB, by properly calculating it. So we get VCC minus VBE by the resistor RB. So here we can see that the current IB is basically determined by the proper selection of the resistor RB, which is the resistor of the base. So we get the current IB, that is the base current, by selecting the proper value of the base resistor. Now in the collector emitter loop analysis, if we do, then we get the collector current is beta times base current. And we have seen that earlier also, that first the base current will be evaluated, then only we'll get the collector current. And we can also apply the KVL equation in the outer collector emitter loop to write down this equation, so that we can get what is the collector to emitter voltage, which is equal to VCC minus IC into RC. if you observe, IC is independent of the resistor of the collector. So here in this equation, there is we do not have any role of the collector resistance as long as the device remains in the active region. So if the operation is in active region, the RC value do not affect the collector current. So RC affects only the voltage of the collector to emitter junction. So here RC plays a role in affecting the collector to emitter voltage but not the collector current. So the important definitions of the voltage, we can see that the collector to emitter voltage, we can say that it is the collector voltage minus the emitter voltage. Now you can see the emitter here is sorted and grounded, so it is at 0 volt. So I can say if we remove this emitter voltage, we just get the collector voltage. So collector to emitter voltage is nothing but the collector voltage. Similarly, the base to emitter voltage, if you see, the base voltage minus the emitter voltage again it is 0. So we get the base voltage only. So emitter voltage is often assumed to be 0 for the simplicity purpose, and it controlled the voltage of the collector emitter, which is critical for setting up the operating region of the BJT in the active region. So we can find the collector to emitter voltage or base to emitter voltage simply as collector voltage and the base voltage, treating that the emitter is sorted and have 0 voltage. So the key characteristic that we get for fixed biased configuration is it is simple to design and it can be implemented easily. It provides control over base current through changing the base resistor. It is sensitive to variation in beta and temperature changes, and it is primarily suited for low power or stable environment. So the fixed bias is only used for low power or stable environment, and it is quite simple in design and implementation. When we talk about the limitations and stability concerns, so it is highly sensitive to temperature variations and transition parameters. So if the temperature changes, the stability will change, and it lack of automatic stabilization, which is make it less suitable for high precision application. So for high precision applications, we do not use fixed bias because it is highly sensitive to temperature, and hence we need some improved configurations like the voltage divided bias, which will address this concern, and we will discuss this in the coming lecture. So what is saturation in transistor? So if we define the saturation, it is basically mean that it is operating at its maximum level. So what is the maximum level? That is saturation level. If you take an example of sponge fully soaked with water, it means that it is unable to hold any more water and it is at the maximum capacity. So in the same thing we talk about the transistor, the current will reach a maximum for that design. So there is no more current it can hold, or the collector to emitter voltage approaches or equal to the collector to emitter saturation voltage. The base collector junction no longer remained reverse bias, leading to distortion. So that is about the saturation. And if you talk about the characteristic, the collector to emitter voltage is 0 volt. The collector current will be at maximum. We say that to be collector current at saturation level. High collector current and low collector to emitter voltage will be there in the transistor operation. So the point where the characteristic curve converge, we can get the Q point. So the collector current with respect to collector to emitter voltage, if we draw the regions, so this is your actual curve and this is your approximate curve. So if we see that where you have the Q point, that is basically the maximum collector current, and it's the maximum current that you have when practically speaking it is at collector to emitter voltage to be 0. So collector to emitter voltage 0, you will get maximum collector current. So treat the collector emitter path as a short circuit in order to evaluate the collector current. So the collector to emitter voltage will be 0, and in that case the resistor of the collector emitter will be equal to the voltage divided by the current. Voltage is nothing but 0 volt of the collector emitter, and collector current is at saturation level. So you do not have any resistor in the collector emitter junction. So these determination of saturation current, we apply a short circuit between collector and emitter. So this is your collector, this is your emitter. We virtually treat to be a short circuit here, and then the voltage across RC, that is the resistor of the collector, we try to estimate, which is equal to the supply voltage VCC. So the maximum collector current or the collector current at saturation will be equal to the collector voltage, which is equal to VCC, divided by its own resistor, that is the resistor of the collector. So this is the maximum collector current. IC should always remain, that is the when you do linear amplification, the operation, the usual collector current should always remain below this collector saturation current. Then only you will have proper linear amplification. So what is the importance of avoiding the saturation? We should avoid the saturation because there will be distortion risk. Saturation disrupts the linear amplification process by introducing the signal distortion. So there will be signal distortion and you will not have linear amplification. So it is better to avoid the saturation distortion risk. If you talk about the design consideration, it ensures that collector current operate well below the highest value of the maximum saturation current for clean amplification process. Practical application, it avoid the saturation, which ensure consistent and accurate signal amplification. So in order to have the signal, to avoid to have the clean amplification process without having any signal distortion, you should skip the collector current below the maximum collector saturation current. So this is the first lecture on BJT biasing. Another 2 lectures we will discuss the other configurations, that is the voltage divider bias or the collector feedback and so on and so forth. Thank you for now. See you in the next lecture.